Now, in today's lesson, the video lesson today, I think you'll find it to be relatively easy to follow, because what we're actually doing is simply taking the things that we've learned, and even seen steps of it, and simply putting them all together. We've seen individual parts. We probably even have an idea how to do this already for some of us, but by the end of the lesson, I'm hoping we can use the first and the second derivatives to quickly and mostly accurately sketch a curve of basic business functions. Now, when we're doing this, one general approach to sketching curves would be simply to start with f of x. We're given some kind of function, and then find our first and our second derivatives. Once we have those are our starting points, and we work from there. Using the first derivative, then, we can locate where our relative maximum and minimum points are. So we find the first derivative where it's equal to 0, and we find our relative extremes. And we can find the y values and then plot these points. Say they were here. Now the next step would be to look at the concavity at these points and also to locate inflection points. If we locate inflection points, setting the second derivative equal to 0 and solving that for x. We can find that point then, let's say it appears here. Then, beyond that, we consider other properties, such as the intercepts. Where does it cross the x-axis or the y-axis? So maybe we work with that and find that they cross here. Well, now we have a really good idea of what the sketch should look like, and we can simply complete the sketch using what we know about concavity, maximum minimums, and inflection points, and the intercepts, x and y intercepts, simply help us to make it a little bit more accurate. So when we complete the sketch, it would look something like this. Now, it's not as hard as it may appear for some of you, and other ones you say, well, this kind of makes sense, it's what we've been doing. Well, that's correct. Now, in working with this, to locate our relative extremes, what we do is set the first derivative equal to 0 and solve for x. So when we're doing this, again, we're going to take the first derivative and set it equal to 0. And the x that we will find from this is considered a critical number or critical value. Critical simply in the sense that it is important. The x value is important. It's where we're going to find the x value of the maximum or the minimum. Then we're going to simply put this back in the original function, do an f of whatever the x is, and that'll give us our y value, or our f of x. And then that's called a critical point because we have both the x and the y coordinate. It's a point, so it's a critical point. It's an important point where the maximum or minimum is. Now, it's possible that it may not be a relative extreme, but usually it's going to be. And in the homework for today, it will be that way. We won't get into some of the odd functions necessarily, although we will see a few of them, where even though you may have it may appear to be a relative extreme, it may not actually be a relative extreme. We'll see an example of that shortly. But in most of the functions we're going to deal with, the slope of the extremes will always equal 0. Now, using the first derivative test for local extremes, and we're supposing that we have an f of x equals 0 at some point. If the first derivative changes from positive to negative at that point A, for example, then we'd say it has a local maximum. Hopefully this makes some sense, that here at A, the first derivative is 0. If we did the tangent line here, the slope would be 0. Now before A, we look at it and say, well, if we took the slope at any of these points along here before, or when x is less than A, the slope is going to be going up. Like they drew one here, it's positive. If we did it back here, it's still going up, it's positive. So it's positive until it gets to A, and then the slope will go down from there. At this point, the slope is negative, it's going down. At this point, it's more negative, so it's still going down. So if you look at the first derivative before A, it's negative. At A, it's 0, and then after A, it's positive. You must have a local maximum because it's in this kind of shape. And of course, the opposite then would also be true. if the first derivative changes from negative, and here it's going down, and the slope all along here is going to be negative. So it's negative until it gets to a, where the slope is 0. And then after a, the slope is positive. The slope will be going up. So then it has to be a local minimum. And hopefully that makes sense from the picture and the shape, the general shape here of the curve. So the first derivative, that's how we could find out if it's a local maximum or minimum, just by looking at the slope around point A. But it's also possible that it does not change signs at A. Then we'd say that the original function has no local extremum. It has no local maximum or minimum. That does happen occasionally. In business, we don't see a lot of these. That would mean that if this was your cost function, usually it's not going to level off and be 0 anywhere, because that would mean that there's the rate of your cost for a specific time is not going up, even though you're producing a little bit more. Now, it can, for one point, happen, so it's possible that you would see this, but usually the function's going to be going up and getting close to 0, and then continuing on, like we saw before in the video lesson from the prior class. But if we do notice here that the slope here at A may be equal to 0, the first derivative is equal to 0, but here it's concave down, and then after A it's concave up, so it actually ends up being that this is a point of inflection, not really a local maximum or minimum. And this other graph is showing the same thing, except of course it's coming down. So it is possible that you could have a slope of 0 and it not be a local maximum or minimum. In this particular case, the slope would, the first derivative being 0, the second derivative will also be 0, meaning it's a point of inflection. Now, to find your local maximum and minimum points, we're going to start with this function here. The first step is simply to put the critical values, to find the critical values in the critical points of your original function, f of x. So, what we do is we calculate the first derivative, and of course, once we put it all together, it's going to be 18x squared plus 3x minus 3. And then we want to eventually set this equal to 0 and solve, and it would be easier to calculate if we factor a 3 out of here. You don't have to. You can simply use this part of the equation and put it into the quadratic equation or the discriminant and solve from there. But if you're going to use factoring, it's also possible to factor the 6 down into 3x times 2x. 3 times 2 is 6, and x times x is x squared. And then that will affect the factoring of these as well. If we use this other form of factoring, we end up saying that this is equal to this. And then we realize that for this to be equal to 0, then 3x minus 1 is either going to be 0 or 2x plus 1 will be equal to 0. So we solve for either of these. And of course, the in-between steps are 3x minus 1 equals 0, so it's 3x equals 1. Here, 2x plus 1 equals 0, so it's going to be 2x equals minus 1. And then divide this by 3 to get 1/3, divide this by 2 to get minus 1/2. So the critical values, our important x values, are at x is 1/3 and x at minus 1/2. So this is going to be, these are the x values of our maximums and minimums. And again, we did that by finding the first derivative and setting it equal to 0. Now, to actually find the critical point, then we have to take our values, our f of 1/3, and put it into the original function. We don't put it into the first derivative because that deals with slope. We want to find the point, the y value. So we go back to the original function. Our f of x is the same thing as our y value. So if we do an f of 1/3, it's going to be 6 times 1/3 squared, which is 6 times 1 over 27, plus 3/2 times 1/3 squared, which is 3/2 times 1/9, minus 3 times 1/3, plus 3. And when we do the math, we end up with 43 over 18. We also then do the second point that we solved for, an f of minus 1/2, and we do the same thing. Remember, we're doing minus 1/2 goes in for all of x, so it's minus 1/2 third to the third power, excuse me. So a minus 3 times and leaves this being minus. But then when we take minus 1/2 and square it, we get positive 1/4. So remember those little things that sometimes trip students up. And when we do an f of minus 1/2, we get 33/8. So now we have there are 2 critical points. At 1/3, 43/18, 1/3 and 43/18. And the second point, again, we use the x value that we found, x of minus 1/2, and then the y value we just calculated to get minus 1/2, 33/8. So now we have our critical points. Now, we want to find if it's increasing or decreasing around the critical points. When we do that, we realize, well, you can find the critical points around the graph just by plotting points. But it's not an extremely efficient way to do this. Since we have 2 critical points, we need to find at least 5 values. We need to find it when it's less than our smallest x value, which is 1/2. Find what it is when it's at 1/2. Find what it is when it's between 1/2 and 1/3, the first x value and the second x value. Find the y value when it's at 1/3, and then also find it when it's greater than 1/3, and draw logical conclusions. Well, again, this would take some time to do. And if we are going to do this, well, what we end up having to do is put in all of these values. So if we're trying to work with this, let's say we're starting at minus 1/2. Well, let's there we go. Minus 1/2 would be about here. We may find a value. Let's just assume my graph doesn't do it 100% here, but let's just assume that it was here. What we need to find to know what's happening, is it going up or down from there? We need to find a value over here somewhere. Maybe it's here. Our second x value is at 1/3, and say x is 1/3 is maybe about here, and maybe we would say that when we plug it into the value, we're going to get a value about here. Well, to know what's happening around it, before the first x value, we said it was here. The next one, we may end up finding the value to be here. That's between the points, and then we need to find another one that is over here somewhere, greater than the point, to know that we're having this kind of thing happening, to know what's happening. We could have something strange be happening when we are working with something like this, possibly. Now, that's not extremely likely, but if we were plotting points, we could actually end up getting something stranger because we aren't looking at the concavity or if it's increasing or decreasing. So it's a way to do it, but it just takes a long time. You can do it if you wish. The other way is to use the factors. The book uses this, but it also takes a while. So you're welcome to use it, but there's easier ways. With this, what they're saying is, again, we have critical points at minus 1/2 and at 1/3. And if we look at the intervals before that and between those two and greater than the last one. But if you take the factors, when we factored the first derivative, we had 3x minus 1 times 2x plus 1. We'll take each of these and find a value when x is less than 1/2, say at minus 1. So do an x of minus 1. Here we would get minus 3 minus 1, which is minus 4, which is negative. Use the other factor, and at minus 1, this becomes minus 2 plus 1. Well, that's also negative. To find the first derivative, what we did is take this times this, and if the answer is, and whatever this multiplied to be, it's the first derivative. In this case, this was negative and this was negative. Negative times a negative is a positive. So that means that the first derivative is increasing because it's positive. So that means from negative infinity to minus 1/2, it's going up. Then we do the same thing in between. This is a little bit confusing. If you If you're not sure about it, don't worry about it. There are easier ways coming very shortly. Again, when we factored it, it was 3x minus 1 times 2x plus 1 to get f prime of x. So we're going to do the same thing. Find out the values of this and the value of this and multiply them together. Find out if it's positive or negative after we multiply. If it's positive, it's increasing. If it's negative, it's decreasing. So here, an easy point to pick would be 0. So we put 0 in for x, and we get minus 1, which is negative. Then here we get 1, which is positive. Minus times a plus is a minus, so it's decreasing. So from 1/2 to 1/3, it's going to be going down. Well, if it's going up to a value and then going down, it must be a local maximum at this point. Then we do the same thing when x is greater than 1/3. Pick an easy value to put in and say x is equal to 1. That when x is equal to 1, we get 3 minus 1, which is 2. It's positive. 2 times 1 is 2, plus 1 is 3. It's positive. So we get plus times a plus equals a plus. So after x is equal to 1/3, it's going to be increasing since the first derivative is positive. So it's coming down to the value when x is 1/3, and then it's going up. So it must be a local minimum. Again, it takes a little bit of time, but you can do it. The book uses this method, so the answers are set up like that. You don't have to use this method unless you want to. Another method is simply to use the first derivative, like I showed you in the beginning of this video. If we calculate the first derivative, what we do is we look at the first derivative when x is less than negative 1/2. And again, we choose a convenient value that makes it easy. So why not use a minus 1? If we put minus 1 into the first derivative, we're going to get 18 plus 3 times minus 1 makes that a minus 3, minus 3. So 18 minus 3 is 12. It's positive. Oops. So so the f of x must be increasing on that interval. Do the same thing for between the points. Choose an x. That's easy, so choose 0. This becomes 18 times 0 plus 3 times 0 minus 3. It's minus 3. So that's negative. It must be decreasing. And then if we work with another easy value when x is 1, again choosing a value that's greater than 1/3, we're going to get 18 times 1 plus 3 times 1 minus 3. And that equals 18. The value of 18 is positive, so it must be increasing on the range of the x ranges from x of 1/3, greater than 1/3 through infinity. So visually then, it must be increasing to the point at x is equal to minus 1/2, which will be a local maximum because afterwards it's decreasing, and then you hit the local minimum because after that it's going to be increasing. So again, this is a little bit faster. It just takes 3 points, but there's still an easier way to do it. And just a reminder, this is really the first derivative test. The way that's easy, that I think is easier at least, some students don't like it, but it's your choice, and that's to use the second derivative. If you calculate the second derivative, you're going to find that the second derivative of x is equal to 36x plus 3. Now, what you can do is go back to your critical points, your maximum and minimum, and see from that, those points, if it's concave up or down at that point. If something is concave up, wherever it's concave up, even if it's at the very bottom of it or along the sides of it, the second derivative is going to be positive. So even if you use the lowest point, it's going to be concave up at that place. And of course, this opposite would be true. If the second derivative is negative, even at the highest point, it's going to be concave down. So what we do is we do an f double prime of minus 1/2, our first critical x value. And so that's 36 times minus 1/2 plus 3, and that equals minus 15. It's negative. So at x is equal to minus 1/2, it's concave down. If it's concave down, that must mean it's a maximum. And then we use the other critical point of 1/3, do a second derivative of 1/3. 36 times 1/3 plus 3 equals 15. It's positive, so that must mean it's concave up. It has to be a minimum. So again, this just seems easier. You can use the critical points. You don't have to use any other points to figure it out. It just works. And again, this comes from the second derivative test. Now, in using this, the second derivative test is defined as if the first derivative at a particular point, call it A, is equal to 0, and then you do an f double prime at that same x value, that same point A. If it's negative, then you're going to have a local maximum. That means it's concave. The second derivative is negative, it's concave down. A is going to be the highest point, the maximum. And of course, then it's the opposite is true. If the first derivative at A is 0 and the second derivative at A is positive, then it's concave up, and that must mean it's a local minimum. So it's an easy thing to remember. It is possible that the second derivative, well, we'll get into that in just a minute. Second derivative can be equal to 0. That will be when we are working with a point of inflection. Now, just simply introduce that inadvertently. To find the inflection points, you set the second derivative equal to 0 and then solve for x. So to find the maximums and minimums, we set the first derivative equal to 0 and solve for x. To locate inflection points, we set the second derivative equal to 0 and solve for x. So, for example, if we were going to graph this particular function, we would calculate the first derivative and the second derivative. And now, if we set to find the critical values of the first derivative, now here, to find the first derivative, we're going to eventually find the inflection point, but first we can find the maximums and minimums with this. If we set the first derivative equal to 0, the first derivative is 3x squared plus 12x plus 9. We can factor a 3 out of that to make this easier and set it equal to 0. Now we can factor this, or you can use the quadratic equation or the discriminant and solve it. But if we factor it, we get 3 times x plus 3 times x plus 1. And then, of course, we set each of these equal to 0 and find that our critical values of x are going to be at minus 3 and minus 1. Now, the critical points, we go back to the original function. We want to find the y values, and that comes from the original function. So, what we're going to do is do an f of minus 3. An f of minus 3, remember the negatives here, since it's x to the third power, the x includes the minus, it's minus 3. So we're going to end up getting negative 27 here. Minus 3 squared is positive 54, and minus 27, well, that ends up being 0. And then an f of minus 1, the other critical value, we'll get a minus 4 when we solve for this, and you can see the math here. So the critical points then are going to be at minus 3 and 0, and the second one is at minus 1. So we did an f of minus 1 and got a value of minus 4. So it's minus 1, minus 4. So then we can go ahead and plot those 2 points. Now, to find the inflection points, what we do is we take the second derivative and set it equal to 0. The 6x plus 12 equals 0. Subtract 12 from both sides, divide by 6, and we get x is equal to 2. So that's the x value of the inflection point is at minus 2. Now, to find where it is on here, we actually then need to come over and do an f of minus 2. Again, anytime we want to plot a point, we have to go back to the original function. So we don't use the second derivative, we use the original function. So an f of minus 2, we put it into that, and we get a minus 2. So that means that our inflection point is at, again, we solved the x of minus 2, did an f of minus 2 to get minus 2. So the point is at minus 2, and we can plot that there. Now, as we're going, we have a really good idea what the graph would look like, but if we check concavity, just to make sure everything is correct, it would be helpful. If we go back to our maximums and minimums, that was at here, the first one here is at -3. If we do a second derivative at -3, we plug that into the second derivative and we get -18. -18 is negative, so that means it's concave down here. So that's going to be a maximum, and that makes sense. Now, we don't necessarily know exactly where it goes other than it will go through this point of inflection. So it could come down like this, it could come way over here kind of thing, but we have a good idea where it's going to go. Now, if we do the second point, when x is equal to -1, do a second derivative of that, we end up getting 6. Well, 6 is positive, so that must mean it's concave up. So from the point of inflection on, it's going to be concave up. Now, again, we don't really know, does it come down like this and go up quickly, or does it come down and spread its way out over here? But we have a good idea of how it's going to be. We figure it's probably 80% accurate at this point, that it's going to do this kind of, it's going to do this kind of shape somehow. Is there any way to make it just a little bit more accurate with very little work? Yes, there is. And that is to calculate the y-intercept. It's easy to do. Whenever you get the y-intercept, that's when x is equal to 0. Well, that just means that you simply need to do an f of 0. So you do an f of 0, you put in 0 for every x. Well, this is going to be 0 plus 0 plus 0. Well, goodness, what could be easier than that, right? And we find that the y-intercept is actually here at the origin at 0, 0. Now, if this function had some constant after it, which it doesn't, but let's pretend if it did. If it said it was all of this plus 3, well, then we would plot the x-intercept up here, and that would change it. If it said it was at -3, we would put it here, and that would change our graph. If it was down here, we'd say, well, it's going to come down like this and over and then up, but we know it goes through here. So if we're going to graph this, we realize that it's going to be symmetrical to the point of inflection. And we have 3 points here, the point of inflection, the minimum, and the y-intercept here. So that gives us our best idea of how it looks. It's going to start at the point of inflection, kind of come down and curve back up and go through that point and go like that. Now, if we were to take this and invert it and put it over this way, we want this side to look like this side, just inverted or upside down. So we know that it's going to come up like this, and then it's going to come down rather steeply again. So just by knowing that one extra point, we've probably made it 90% accurate. It's still not perfect, but if we want a perfect sketch, we can go back and use a computer or plot more points to find out what it is. But using calculus, we can quickly find this. Using the first derivative, we quickly find the maximums and minimums. Using the second derivative, we quickly find the inflection points. Solving for the the y-intercept is easy, and that gives something that's probably 90% accurate. If you really like to do math, you can also plot the x-intercepts. The x-intercepts would be when f of x is equal to 0. So you'd set this whole thing equal to 0 and then solve to find out what those x values are. When you get into x cubed, it makes it harder, so I usually don't bother saying just doing the y-intercept is fast and easy, so go ahead and do it. The x-intercept would make it a little bit more accurate, but in this specific example, it just so happened that we found the x-intercepts because the maximum is there and the y-intercept is here is the second x-intercept. So hopefully this isn't too hard. This just kind of puts everything together, and the homework gives you a chance to practice this. And even though there's not a lot of problems, they take time to do, as you can see. Calculating the first and second derivative, finding when each is equal to 0, and graphing just takes some time. So the homework is, of course, also on Moodle. And have a good day. We'll see you in class.